Hi guys, today in this video we are moving on to the second class on functional analysis. The topic is about quotient spaces. So already we have defined vector spaces and we have the one paper on linear algebra. From that we have almost all the theorems we studied about vector spaces and all. Now we have the operations, vector addition, scalar multiplication, and we have the set theoretic subset subspaces, diagonalization process and everything. So it is very usual to think if we can find something analogous to the division of a set. So analogous to the division of a set, one can think of partitioning the set or partitioning the vector space into subspaces. So in that point of view, we have a vector space or a linear space and we have a subspace, and connecting with that subspace or making that subspace as the basis for something, we are going to partition the whole vector space. So that is the idea of quotient spaces. So in order to partition a particular set, we should have some equivalence relations and all. So we will form some equivalent relation on the sets, and we are forming some subspaces or new linear structure with the help of cosets and all. So actually it is a very interesting journey. So in this video we will just move on to the things and concepts of quotient spaces. So we have first the definition of cosets of a subspace. So let E be a linear space and E1 be its subspace. The set X plus E1, defined as set of all X plus W, where W element of E1 is called the coset X. That is the coset of E1 with the representative X, okay, where X is an element of E. So in fact cosets are also called affine subsets in some other textbooks and all. So we have the definition of the coset. Now we will think of some examples of cosets. So we will think of what we know, what we can see in. That is, we will first think of R2, the Euclidean space with 2 dimension. That is the plane actually. So what is a subset? In Euclidean plane of dimension 2, that is in R2, we have 3 types of subspaces actually, not subsets, subspaces. First is the trivial subspace, that is the 0 subspace. So that is a subspace. Then we have the whole set, that is R2 itself, that is also a subspace. Other than that, if we are thinking of non-trivial proper subspaces, non-trivial proper subspaces of a plane, Euclidean plane, are all straight lines passing through the origin. We know that. So here we have a coset. We are taking one line, capital L, which is passing through the origin, and we are going to construct cosets of L. By passing through that origin, we are constructing the cosets of L. So the coset of L is actually the set of all lines parallel to capital L. So likewise in R3 also we can think of some subspaces. That is, consider R3 the Euclidean space with dimension 3. A plane P passing through the origin is a subspace. A line passing through the origin is also a subspace. Then we have the trivial subspaces and the improper, the A itself or E itself. So in this case, if I am taking a subspace that is a plane passing through the origin, what will be the coset of that plane? That will be the set of all planes parallel to the plane that we are taken. Okay. So we will have an example of a coset. I have just come up with a diagram. So here we have R2, that is the Euclidean plane. So here the red line is L, the subspace, a line passing through the origin. Then the cosets of L will be all the parallel lines which are parallel to the line L. So that collection of cosets, the yellow lines I have denoted it with. So now we know what is a coset and all. So we have some 4 or 5 important results on cosets that we have to taken into consideration, so that we could define an equivalence relation with that. Okay, so result 1, we have E be a linear space, even be a non-trivial proper subspace of E. So I have already told what will happen when it is a trivial subspace. If it is a trivial subspace, then the coset will be the set of all points of V, that is V itself. So nothing special with it. If the subspace is V itself, then the coset will be what? The 0 point, the 0, only the point 0. So that is nothing to deal with. So all the things we have to deal with is non-trivial proper subspaces. So I am taking a linear space E and even be a non-trivial proper subspace of E. Then I am having the result, if I am taking any two elements x and y element of E, we have the coset x plus E1 equal to coset y plus E1 implies and implied by x minus y element of E1. So what we mean by that? That is, if we are taking two cosets, if they are equal, then there will be the if and only if condition, exactly x minus y, the difference between the representative elements x and y should be in the subspace. Then we can say that two cosets are identical or two cosets are the same thing. So that is what we are going to prove in this result. So suppose x plus E1 is equal to y plus E1. So this is an if and only if condition. So we have to prove in the to and fro manner. Okay. So first we will suppose that two cosets are equal. That is, x plus E1 is equal to y plus E1. So where E is a non-trivial proper subspace. Now if A is equal to B, then A subset of B and B subset of A. So likewise we can say x plus E1 subset of y plus E1 and y plus E1 subset of x plus E1. So I'm taking an element W1 element of E1, and we have x plus W1 element of x plus E1 by the definition, and x plus E1 in turn is an subset of y plus E1. Okay, so there will exist some W2 element of E1 such that x plus W1 equal to y plus W2. So from that I can have x minus y. What will be x minus y? X minus y will be the difference of W2 and W1. Now E is a subspace and E is closed under addition and subtraction. So this W2 and minus W1 will be some element of E1, some W3 element of E1. So we got what? If I am taking two cosets are equal, we are getting that the difference of the representative elements x minus y will be in the subspace. So the one part is over. Now we are moving on to the converse part. So conversely, suppose that x minus v element of E1. Okay, so we have to prove that the two cosets are the same. So I am taking, if I have to prove that A is equal to B, then I have to prove that A subset of B and B subset of A. So I will take one element from A and I will prove that it is in B likewise. So here I am taking Z element of x plus E1. Then Z will be equal to some x plus W1, where W1 is an element of the subspace E1. Now we are taking x minus y as some element of E1. It is already in the assumption. So x minus y is equal to W2 for some W2 element of E1. Now gathering all the information we have, so Z is equal to x plus W1, that is equal to y plus W2 plus W1. That is, I am substituting x for here. Now that is equal to y plus W1 plus W2. So here it is a subspace, so we can apply all the associative conditions, commutative conditions and all. So applying the associative condition, we can have y plus W1 plus W2. Again, E1 is a subspace, so the linearity conditions are there. So W1 plus W2 will be some W3. So Z is equal to y plus W3, where W3 element of E1. So that implies x plus E1 is subset of y plus E1. So I am taking an element Z from x plus E1 and I am seeing that it is in y plus E1. So we get the subset condition. So similarly we can prove that y plus E1 is contained in x plus E1. So from both equations I can prove that x plus E1 is equal to y plus E1, hence the result. So this is a very important result, because using this result we are going to define the equivalence classes, because in order to form the quotient space we have to partition the entire vector space into subspaces or into cosets. So by partitioning itself, the equivalent sets comes into our mind, no? So according to result 1, two elements x and y of E determine the same element of E by E1 if and only if the difference of x and y are in E1, that is in the subspace. So this is the point of view taken when defining E by E1 by the set of all equivalence classes of the equivalence relation tilde on E, defined by x is related to y if and only if x minus y element of E. So the partitions are well defined here, and we got yet new elements called cosets to deal with. So apart from the vector addition and scalar multiplication defined on vector spaces, if we could define some sort of addition of cosets and scalar multiplication of cosets, we can easily construct yet another linear structure or yet another linear space called the quotient space. So before going to the definition of the quotient space, I would like to present before you some more results which are essential for the well-defined operations, coset addition and scalar multiplication of cosets. So we are moving on to the result 2. So result 2 says that E be a linear space and even be a non-trivial proper subspace of E, then if x is element of E, then the coset x plus E1 is E1 itself. That implies x element of E1. Okay. So I will say once more, if E be a linear space, even be a non-trivial proper subspace of E, then for any x element of E, we have x plus E1 equal to E1 implied by x element of E1. So if the representative element is in the subspace itself, that is the coset is the subspace itself. Okay, we'll go to the proof. It is very trivial proof, but still we will just go through that. We are taking the first part, that is x plus E1 is equal to E1. Then we can say that is x plus W1 is equal to W2 for some W1 and W2 in E1. So I am taking x as W2 minus W1. Again, E1 is a subspace, so I can apply the linearity condition and we'll get x is equal to some W3 for some W3 element of E1. That means x is in E1. Conversely, suppose that x is in E1, then we know that 0 plus E1 is equal to the coset 0 plus E1 is equal to the set of all 0 plus W or W element of E1. So that is the set of all W such that W element of E1, that is E1 itself. So from the result 1, I can apply the result 1 here, that is x plus E1 is equal to 0 plus E1, that is implies x minus 0, that is x element of E1. So we got x element of E1 here. Now we have to remark the subspace E1 or the elements of the subspace work as identity in the case of coset addition, because it is making no much change in the process. Now one more result we have on cosets is two cosets of a subspace either coincide or they are disjoint. This is what I have told you before, that is the idea of cosets are the idea of equivalence classes. So already we know that equivalence classes will either be identical or disjoint. So the same idea here. So already I have defined what will be the equivalence relation, like, so you can check whether it is equivalence relation as a homework, check whether it is reflexive, symmetric and transitive, etc. That you can do it as a homework. Here I am just focusing on the fact that two cosets of a subspace either coincide or they are disjoint. So moving on to the proof, we are taking a linear space E and E1 be a non-trivial proper subspace of E. If I am taking two cosets x and y, so x is equal to x plus E1 and y is equal to y plus E1, be two cosets of E1 where x and y element of E1. If they are disjoint, there is nothing to prove, we are done. If they are not disjoint, suppose that there is some z in the intersection. So we are taking z element of coset x intersection coset y. That means z is in coset x and z is in coset y. So x plus e1 is equal to z equal to y plus e1. Now z minus y and z minus x will be in E1 by result 1. So since E1 is a linear space, we can apply all the linearity conditions of addition and subtraction. So using that, we have z minus x minus z minus y is actually y minus x. Y minus x is in E1. Now we are taking a point A from coset x. Then a minus x will be in E1. Then again by the linear structure of E1, we can have a minus y also is in E1. That means a is in the coset y. So that means coset x is subset of coset y. Similarly, we can prove that coset y is contained in coset x. So therefore the two cosets are identical. So we have to note that coset x is equal to coset y if and only if x minus y element of E1. Already we have told that. Now we have going to the result 4. Here in this result 4, what is happening? We are defining coset addition and scalar multiplication with cosets. So that is important with that. So let E be a linear space and E1 be a non-trivial proper subspace of E. Then if x1 plus E1 equal to x2 plus E1 and y1 plus E1 is equal to y2 plus E1, where x1, x2, y1, y2 are all elements of E, we can define the addition by x1 plus y1 plus E1 equal to x2 plus y2 plus E1, and cx plus E1 is equal to cx1 plus E1 equal to cx2 plus E1. So moving to the proof, suppose x plus E1 is equal to x1 plus E1 equal to x2 plus E1 and y1 plus E1 equal to y2 plus E1. So applying the linearity conditions of E, x2 plus y2 minus x1 plus y1 equal to x2 minus x1 plus y2 minus y1, the associativity conditions. So x2 minus x1 are in E, so that difference will be some x3, and y2 minus y1 will be some y3. Then again these both are in E, so x3 plus y3 will be some w element of E. So by result 1 we have x1 plus y1 plus E1 equal to x2 plus y2 plus E1. So the coset addition has been defined here. Now moving on to we are taking a scalar c from the field. C x2 minus C x1 equal to C of x2 minus x1. Again x2 minus x1 is some x3, so C x3 element of E1. This implies that Cx1 plus E1 equal to Cx2 plus E1. So the scalar multiplication and addition of cosets are defined in this result. Now we are going to define the quotient space. So we are now equipped with all the theorems and all the properties of the cosets, and we have very well defined two operations have with us. We have coset addition and scalar multiplication of cosets. So with that we are going to define quotient spaces, and we will say that the quotient space is a vector space. So let E be a linear space and E1 be a subspace of E. Then we define the quotient space E by E1 to be the set E by E1, or some say E mod E1. So we will use E by E1. So E by E1 is actually the set of all x plus E1, that is coset x, such that x element of E. That means that the quotient space is the collection of all cosets of E1 with representatives from E. Now result 5, the quotient space of a linear space and its subspace is yet another linear space. So we are going to construct a linear structure based on the linear structure on quotient space. Here the elements are all cosets, that is the only difference. So we define this linear structure with two binary operations, namely addition of cosets and scalar multiplication of cosets, as follows. So coset x plus coset y is equal to coset x plus y. Then a into coset x is equal to coset ax. Here identity will be the coset 0, which will be E1 itself, the subspace itself, that we have proved in result 2. Then other norms of the vector space or a linear space can easily be proved with these two well-defined operations, and that also I am giving you as a homework. Now we will move on to the dimension of the quotient space. So the dimension of a quotient space is called codimension of E1 with respect to E, and we denote codimension as dim E by E1 or codim E of E1 with the respect to E, or simply codim E1 if it is obvious which space E it is referred to. Now usually in functional analysis we are dealing with infinite dimensional vector spaces, but once we are having finite dimensional vector spaces, then the dimension of the quotient space can be taken as dimension of E by E1 is equal to dimension of E minus dimension of E1. Maybe you have come up with quotient spaces in abstract algebra paper in first semester, and otherwise also I think the notion and concepts of the cosets and quotient spaces are clear to you. So thank you for watching.